Hello. So today we will speak about digital to analog converters. So what we did so far was the analog to digital converter. So we will see that the digital to analog converter is much simpler. So there are different ways to implement this circuit. So what we want to do is to start from a digital binary number expressed in the form of 0 and 1s and to reconstruct a level of voltage which can vary with continuity between a maximum and a minimum, but with some constraints. So if we have, for instance, an 8-bit number, it means that we have 8 binary digits. So the only possibilities for those digits is to be a number which is 0 or 1 or 2 or 3 or 255 converted into decimal forms, because there are only 2 to the n possible combination of 8 bits that can have two values, 0 and 1, and this means that we can have only 226 different level of voltages. So our resolution in the voltage that we want to represent is limited to the number of bits. If we want to have a higher resolution, then we have to have a higher number of bits. So there are different ways to do this. Let's see this one, which is very popular. It's called the R-2R ladder. So resistor to resistor ladder, which is this thing here, you see. So here what we have is a circuit made only of passive components, resistors, having a specific value. So it's like this. The first one here, the one which is connected to the ground node, has a value of 2R. All the others here have a value of R, and all the ones here above are a value of 2R. R can be any value, so you can choose it. Then here you have some inputs. We call them A0, A1, A2 till an minus 1, which means that they are n in number, so our n bits, and this node here is our output voltage. So what do we connect here at the A inputs? We connect another source of voltage we call reference voltage, Vref, and the logic is that we can associate a 0 when this Vref voltage is not connected, or to better say, when this node or this or this or this are connected to ground, and we associate a 1, a logic 1, when we connect these inputs to the Vref source. So it is as like as if we have something like this. We have another battery here connected to ground. Here is the plus, this is V reference. Then here we have a switch like this and like that. So one wire is like this, the other one is like that, and so on till the last one. So basically those switches would be transistors, of course, and they will connect the inputs either to ground or to VREF. So ground means 0, VREF means 1, and the configuration of those bits is the digital number. Okay, so let's try to see how this thing can work. So we go to the blackboard and we try to replicate a couple of cases. Okay. So I just copy the first part of the circuit. It was like this. So here we had ground. This resistor was 2R. This one was 2R. This one was our input we called A0. Then we had a lot of other stuff, but let's try first to analyze the case. I call this the output of a simple 1-bit DAC, digital to analog converter. Okay, so let's see what happens in this case. Okay. So we have to draw this circuit. So like this, like this, like this. So we start from this thing here to be 0 volts ground. So A0 equals 0 volts, to R, and then let's evaluate the output, the output. I just changed the shape of this circuit, but it's the same. So here we maybe better recognize our voltage divider. So we can write the output of the circuit as the function of the input voltage for the given resistors. So the output voltage V out is V input, we call it A0, multiplied the resistor at the bottom, which is 2R, divided the sum of the two, 2R plus 2R. And so this is A0 divided by 2, simply. So we cancel the 2, we cancel the R, and only this 1/2 factor remains. So now we have two cases. The case is A0 equals 0, which makes V0 equal to 0, and the case A0 equal V reference, which makes V0 to be equal to 1/2 V reference. So it's a 1-bit digital to analog converter. We have two cases and two different outputs, 0 and 1/2 of VREF. And this is basically what this thing is saying here. So the output is V reference, the number for 1 bit. This number can be either 0 or 1, divided 2 to the n, where n is the number of bits. So we have 1 bit, 2 to the 1. So this thing can be either 0, when the number is 0, or vref divided by 2 when the number is 1, for 1 bit. So now let's try to calculate what happens if we implement a 2-bit ladder. Okay, let's go back to the blackboard. Okay. So now we want to analyze this circuit. So we have the first resistor, 2R, then this one, 2R, this is a 0. So now we have to be careful because this resistor has a value of R, then 2R and A1. And now we call this output. So this is a 2-bit digital to analog converter. Now we have 4 cases. So let's first try to understand the case for which A0 equals 0 and A1 equals 0. So this corresponds to the binary number 0, 0. Okay, so then we have to modify this circuit. This circuit will become like this. To R, then it's connected this way. R to R, and here we have V0. So let's try to redraw the circuit in a better way. I start from this node here. Let's give it a name. Let's call A, and also let's put B. So here we have this resistor to R, then we have this resistor to R, then we have this resistor R, and this is the node A. Then we have another resistor like this, whose value is 2R, and this is the node B, which is also our output, the output. So we want to understand this case. Okay, so the first case is very simple, because we see that in this circuit there are no generators, and so of course the output should be 0. So the first was simple. So now let's try to do the other cases. There are other 3 cases. So I take this because we need it, and let's try to do the others. So let's try to analyze the case A0 equals 1, logic 1, let's say, and A1 equals 0. So we have to redraw the circuit. So it's like this. 2R, then A0 equals 1. This time A0 is connected to a generator. Let's put it like this. So this is V reference. Let's also put the name on the nodes. Where is it? Here. This is the node A. Then we have our resistor R, and this one is like this. R and 2R, and the output is here, B. So now this is the voltage we want to calculate. Okay, let's see how we can do this. Okay, so in this case I will try to take advantage of some series and parallel formulas instead of doing all the node analysis, because I see that this circuit is, let's say, quite simple. So I can realize that this resistor is in series with this one. So if I'm able to replace this with the equivalent resistor, and it's very simple, then the equivalent resistor will be in parallel with this one, and then I will have a voltage divider between this one and the equivalent resistance that I will put here. So therefore I can calculate the voltage at the node A, and if I know the voltage at the node A, then I calculate the voltage at the node B by considering this voltage divider. So let's try to do this. So from this circuit I go to another one, which is this one. Where I modify this thing here like this. Okay. And here we have the equivalent resistor of this and this one. So we need to summate the two, and it's 3R. Then this one goes in parallel to this one. So there is one formula we know about parallel resistors, which says that 1 over R equivalent is equal to 1 over R1 plus 1 over R2 if we have two parallel resistors. So it is useful to arrange this formula in this way. So this implies that R equivalent is R1 multiplied R2 divided R1 plus R2. We just need to do some little algebra. So this thing is quite handy because it happens lots of time that we have to calculate the parallel of two resistors. So now let's calculate the parallel of those two resistors. So we calculate this R equivalent, which is 2R multiplied 3R divided 2R plus 3R, and this thing is 6R squared divided 5R, which is 6/5 of R, and therefore we can replace those two resistors here with this resistor, 6/5 of R. So now we can calculate the voltage at the node A. So VA is equal V reference multiplied this resistor 6/5 R divided itself plus this one 6/5 R plus 2R. Now I have to delete something, so let's delete this. Okay, so let's try to proceed with this. So VA equals, okay, so it's, if I multiply by 5, so it's V ref multiplied by 5 at the numerator and the denominator, 6R plus 10R, and this makes V reference 6/16, and the R is cancelled. So 6/16 is also the ref multiplied, let's say 3/8. So this is the voltage of the node A. So let's write it here for later. So VA is V ref multiplied 3/8. Okay. Now we have to calculate the result of this voltage divider. So let's do it. So now we have the voltage VB, which is actually V output, equals VA, which is V ref multiplied 3/8. So this resistor divided this plus this, 2R divided 2R plus R. So it's V ref 3/8 multiplied 2R divided 3R. This goes away, then this goes away, and this is 4, so it's 1/4 V ref. Finally, I'm always in pain when I do this kind of calculations. because it's very easy to make a mistake. So let's see what we did. So let me remove something that we don't need anymore. So we don't need this. Delete. We don't need this too. Delete. So we have that with this configuration here, which corresponds to the binary number 0, 1, then the output is a quarter of VREF. Okay. So let's try to make only another one, because you see this thing is very repetitive. So we have to compute 4 cases, but just to give an idea, we computed the first one, which was very simple because it was 0. Then this one is 1/4 of VREF. So let's try to compute the case 1, 0. Let's see what we have. So I copy this one, copy, then I paste it here. So we did the case 0, 1. Let's try the case 1, 0. So the lower bit is A0 and the higher bit is A1. So when you have more bits, there is also this nomenclature. The lowest one is called the least significant bit, LSB, and the higher one is called the most significant bit. In the sense that if you change, if you have a number like this, so 1, 0, 0, 0, 1, 0, 1, 1, 1, if you change only this one, then you change the number a little. But if you change this one, you change the number dramatically. So this one has more significance than this one. So let's try to do this one. So now this time A0 is at ground. So we have 2R, which is this one. A0 is connected to ground, so it's like this. Then we have the resistor R. This is the node A. Then A1 is connected to VREF. So let's do it like this. Okay. So then we see better. So this is the node A. This is the node B. This is the resistor R to R. And here we have our battery VREF. And this one is the output. So we want to calculate the voltage at that node. Is that correct? Let's check. Okay, A0 goes to ground, resistor, A1 goes to VREF, 1, 0. Okay. So this one is quite simple, because we can easily see that those two resistors are in parallel, and therefore we can substitute them with the equivalent resistor. So, and this would be 2R multiplied 2R divided 2R plus 2R, which makes 4R squared divided 4R, which is R. So we can replace those two resistors with one resistor like this. And this is the node A. Okay. Now it's easy because those two resistors are in series, so we can replace them with their equivalent resistor, which is the summation of the two. So here we have this. We have 2R, and now we have this voltage divider, so the output is V reference multiplied this resistor to R divided the sum of the two, and this is 1/2 Vref. So if you want 2/4 Vref. So we have those cases. The case for which 0, 0 makes 0 volts, the case for which 0, 1 makes 1/4 of Vref, the case for which 1, 0 makes 2/4 Vref. So just to be complete, let's write it like this: 0/4 Vref. And we don't do this, but you can imagine that if you do this, then you will have the case 3/4 Vref. So if you want to make a scale, so it's like this. Here you have 0, 4, 0, then you have 1/4, 2/4, 3/4. So we have 4 voltage levels. So if we do this with n bits, then you have n voltage levels.